Presenting SplatFlow, Self-Supervised Dynamic Gaussian Splatting in Neural Motion Flow Field for Autonomous Driving, at CVPR 2025. Original 3D Gaussian splatting struggles with dynamic urban scenes due to limited temporal modeling. To address this, methods like Street Gaussian introduce separate Gaussian models for static and dynamic components using object bounding boxes for detection and tracking. However, these methods rely on accurate object-level supervision, such as 3D detectors, limiting their scalability in real-world settings. Self-supervised methods like PVG model dynamic scenes without relying on 3D bounding boxes by introducing time-dependent Gaussian primitives. However, they struggle to learn accurate motion purely from rendering losses, which limits their overall performance. Therefore, in this paper, we propose a self-supervised dynamic Gaussian splatting method for accurate scene reconstruction and high-quality novel view synthesis including RGB, depth and optical flow images. We introduce neural motion flow fields to model dynamic objects' motions as continuous flow fields, which also enables scene decomposition into static and dynamic components. In addition, we enhances the motion representation by uplifting 2D features distilled from foundation models to 4D spacetime through optical flow synthesis. The core of SplatFlow is the neural motion flow field, which captures how objects move through space and time using a set of implicit functions that represent dynamics as continuous flow fields. This enables fine-grained, point-level motion modeling. NMFF is built from 3 supervision signals. First, we pre-trained NMFF priors from 3D LiDAR sequences. Second, we optimize NMFF to learn temporal status transitions of dynamic Gaussians through video rendering. And third, we distill motion cues from 2D optical flow foundation models to further enhance NMFF. These components jointly enable NMFF to model fine-grained motion in dynamic scenes, without manual annotations. We leverage the rich geometric structure in consecutive 3D LiDAR frames to pre-train NMFF with a strong motion prior. By compensating for the ego car motion, we ensure that NMFF learns only the motion of dynamic objects. As a result, the predicted 3D motion flow excludes ego motion and focuses purely on object dynamics. This enables NMFF to effectively decompose dynamic and static elements from LiDAR points using a simple motion threshold. For each LiDAR frame, we apply a threshold to the NMFF predicted motion at each point, allowing us to separate dynamic points from static ones. Static points across frames are then merged using the known ego car poses. For dynamic points, we aggregate them into a common reference frame by combining ego car motion with the NMFF predicted object motion. We represent the static background of the driving scene by static 3D Gaussians. The 3D Gaussians are initialized using the merged static LiDAR points. We represent dynamic objects in the driving scene using 4D Gaussians. These 4D Gaussians are initialized from dynamic LiDAR points that have been aggregated into a reference frame, improving density and completeness of dynamic object representation by combining observations from multiple viewpoints over time. We use NMFF to model how each 4D Gaussian moves through time. To render an image at a target timestamp, NMFF transforms the 4D Gaussians from the reference time to the target time. We then perform image rasterization using both the 3D and 4D Gaussians. Our pipeline renders RGB, depth, and optical flow images. We optimize both the Gaussian attributes and NMFF using image-based rendering losses. To further enhance NMFF's motion representation, we introduce an optical flow rendering loss that distills knowledge from a 2D foundation model, bridging 2D motion cues with our 4D space-time representation. The top graph shows PSNR performance on dynamic scenes from Waymo and Kitty, evaluated on image reconstruction and novel view synthesis. SplatFlow consistently outperforms all baselines, highlighting its strength in modeling dynamic content and producing high-fidelity renderings. The bottom left graph shows PSNR on dynamic objects across 4 Waymo sequences. SplatFlow consistently outperforms PVG, demonstrating superior performance on complex, dynamic content. The bottom right graph evaluates PSNR for novel view synthesis on the Kitty dataset under different training data sizes. We compare performance across multiple train and test splits. SplatFlow consistently achieves the highest scores and maintains stable performance as training data decreases, demonstrating strong generalization and making it highly effective even in data-limited scenarios. We present the visual comparison with baselines of novel view synthesis on the Waymo dataset, including zoom-ins of dynamic regions. Unlike baselines that suffer from ghosting and blur, our method preserves high-quality details. Additionally, we demonstrate our method's ability to decompose dynamic objects. Compared to the baseline, our approach more clearly separates dynamic elements from the static scene, highlighting its effectiveness in motion-aware scene understanding. We evaluate novel view synthesis under a more challenging setting on the Waymo dataset by introducing new ego-car trajectories. Specifically, we shift the original trajectory by 0.5 meters upward, downward, leftward, and rightward to simulate unseen viewpoints. Despite these shifts, SplatFlow successfully renders high-quality images, demonstrating strong generalization and robustness to viewpoint changes. We present novel view synthesis demos on both the Waymo and Kitty datasets. Our method produces high-fidelity renderings that preserve fine details, especially in dynamic regions where existing methods often struggle with stability and consistency. SplatFlow accurately reconstructs these challenging areas, resulting in more realistic and coherent novel views. We visualize rendered results on the Waymo dataset and the Kitty dataset, including RGB, optical flow, and depth. As shown, SplatFlow produces sharp and detailed outputs across all modalities, capturing clear and dense motion and depth information in complex dynamic driving scenes. Thanks for watching.